Now we'll start. So today we're going to finish up what we did. Is this camera in your way?
No, your head is in my way.
Ah,
Let me move over.
Yeah, my head moves around quite a lot, so you might want to resituate. But I'm going to be here quite a lot. So, okay. So let's see. Today we're going to go through Kepler and Newton, but we're going to finish up some stuff. Okay. So first numerical homework assignment was due this morning. Looks like I got one from just about everybody, and it looks like everybody did good. Is there anything about that assignment or the process that anybody wants to talk about? Because I'm not going to go over it. I'm going to try to go over most of the assignments because I feel like ironing in all the things that you learned when you were doing stuff is good, but this is a pretty straightforward assignment, so I'm not going to really spend any time on it. I'm going to finish up reading 1 to pick up the last couple of questions that I missed, and I'll go through reading 2, and I'm going to try to do those things quick because I tend to talk a lot. And then I'll talk about parallax. I'm going to do all those things kind of quick, and I'm going to actually blast through parallax kind of fast because I've already talked about it and it's not very complicated. This other stuff that I'm going to talk about today is more complicated, so I want to focus on that, on the stuff that you need me for. You don't really need me for parallax, but you do need me for why a sphere counts as a point at the center. I'll talk to you about that. So, okay, so let's see. Oh, this is from yesterday's reading. Let's pick up today. Oh, no, that's everything. Okay. Radial and transverse velocity. Let's see, where's my time? 1:23. Okay. So we talked about that a little bit. So the radial velocity is just the one that's relative to me along my line of sight. So if I've got a star, it has 3 velocity components. One of them is along the line of sight. We call that the radial velocity. And the other 2 are in the plane of the sky, and that's the transverse velocity. And we talk about the transverse velocity not so much as a velocity, but as proper motion, which is the angle change as a function of time. Let me know if you need me to explain that a little bit better. I'm not actually going to need to talk too much about transverse and proper motion at the present moment. The benefits over a parsec over an AU or a light year are scale and its similarity to the geometry where we derive it from. So a parsec is a more fundamental unit because it's geometric. And I'll show you why in a second. Okay, does the celestial equator shift? It does. So the celestial equator, so the celestial equator is here. Think the sun relative to the celestial equator moves, but the celestial equator does not. It sticks around and is in the same orientation all of the time. Can we use parallax? Can we use parallax using arc lengths? So, the arc length is just this. We usually don't need to do that. So one of the nice things about arc length is it's got a very easy mathematical value. So if the arc length, we call that S, and this is an angle theta, and we have a radius r, the arc length S is simply r times theta, where theta is in radians. So that would make this math simple, and you don't need to do the small angle calculation, but realistically, this curved thing is not usually what I want. Usually what I want is the straight distance between 2 objects. Let's see. Is the precession of the equinox a problem? No, because we know about it and we can take it out. We just figure out how much the precession is and we take that out. I'll talk about precession in a section. Does precession have any effect on climate change? No, really, it's us. We're doing that. It's just all the carbon. It's just thermodynamics. Climate change is really straight thermodynamics. The photons can't get back out, so it heats the planet up. The actual pointing of the planet doesn't change very much. Now, someone did look at the motion of the Earth through the galaxy and has some link between mass extinctions and where we are vertically in the galaxy. But I kind of call BS on it. So let's see. Is alt-as still used since it's relative to the observer's position? Yes, it's relative to my position, but it's still useful because it's relative to my position. So that makes it easier to deal with. Okay, can we only use parallax for things close to Earth? How close? I'll show you that in a second. Okay, let's go through parallax real quick because that's the last couple things. Parallax and precession. Okay, so parallax. Well, let's talk about precession first. So when I have the demo room is just right down there. It has all of the best toys in it. It's got the funnest toys, and they have some really nice gyroscopes. Have you ever played with a gyroscope and spun a gyroscope really, really good and hung it from the end and watched it spin around? Has anybody done that before? So if you have something spinning and you try to twist it, it's going to rotate because it has to keep angular momentum the same. So if I have an object with an angular momentum vector like this, that means it's spinning around like this, right? Now if I add a torque on it and I try to twist it like this, then I'm adding another angular momentum vector like this that's coming out of the board, right? So I've got this angular momentum vector and this angular momentum vector, and to keep this one wants to stay the same, but I'm doing this, so we have to add some of this to counteract it, and it's going to precess. So there will ultimately be a net torque on the object. You'll go. I don't need you to understand how those details work. You'll go through them when you get to mech. If you do that, but we can compute it. So the physics is pretty straightforward, but I'm not going to go down that rabbit hole because it's dark and there's rabbits in that rabbit hole. But we can talk about exactly how much the precession is going to be as a function of time, because we know what the torques are on the planet. So the biggest torque on the planet comes from the sun. So the planet's not perfectly round, so there's a little bit of a torque on it from the sun. And we can sort out how much that torque is. So the change in RA in right ascension is going to be some number m plus some function of the RA and dec. And the change in declination is going to be some function times a function of the inclination angle. This is all kind of hairy. And this m and n are both polynomials of the time. This is ugly. How do I use this thing? So, okay, the way this is written down, and this is in the book, big T is the time in fractions of a year over 100. So if I want to know the precession since the year 2000, I would take the year, say, 2001, plug it in for T, and divide by 100. So for 1 year, big T is 1 over 100. And then I plug it into these two polynomials that you can't see very well, but this one is 0.5T. Here, I'll write this up big. I'll write up the bit that I care about, actually. The change in declination, the change in declination is equal to some number m times the cosine of the right ascension. And remember, declination or right ascension are just angles. The right ascension is the angle from the vernal equinox, which is just a point in outer space, and the object. And the declination is the distance in angle from the equator up to the object. So if I just sit here, they'll move because the Earth kind of wobbles as it spins. So m is equal to what? It's equal to 0.5 times t plus, what is that number? 10 to the minus 4 times t squared times 10 to the minus 5 t cubed.
That's n, right?
Okay, cool. The point's the same. Better to make. Plus 10 to the minus 5 t cubed. Okay. So if t is 1 year, then big T is 1 over 100. So I'm going to look at this horrible equation, and I'm just going to throw out these two terms. Right? So if I'm looking at 1 year, 0.01 squared is a really small number, and then I multiply it by this other really small number. 0.01 cubed is an even smaller number. So we can just think about the amount of precession as a half a degree times the fraction of the year. So we're at like 0.05 of a degree per year, which is really not very much. So the fraction is actually very small. And I had, let's see. So precession, I don't need to talk about precession at all, really. But when you see things, the reason that we need to bring it up at all is you'll see coordinates with a J2000. Or when I was a kid, 1950, but they don't use that anymore because the 2000 is more recent. Most things we use J2000. So this is the Julian year 2000. That just means 2000, like a couple years ago, right? A lot of years ago, I think that was before most of us were born, right? But not a ton. So everything is relative to this date because we need to describe the coordinates as they were on that date because they've moved. So we don't want to use the constantly updated times, we just use the coordinates here. So when you're actually going to observe something, you look up its RA and DEC for the Julian year, and then sometimes you got to correct a little bit for whatever the precession is. None of you are going to be using telescopes that have that kind of accuracy anytime soon. So when you do, come back and learn all this stuff. That's not what I care too much about right now. But that's what it's for. And I'm actually, because I want to get through other stuff, I'm skipping that. And I'm skipping that. Okay, parallax. So we've talked about parallax a little bit, right? It's the change, it's the apparent change in where things are based on you moving around in space. So as I move from one side of the planet's orbit to the other side of the planet's orbit, if I'm looking at an object, the background stars are at infinity, and it looks like this object effectively moves from one point to another by an angle p. And the distance to that object, the formula is actually super easy. So the formula is really just geometry. We have an angle here, but I'll show you where this number comes from. So this is my angle theta, this is my distance r, this is my distance, let's call this capital D, keep it consistent, and this is my baseline r. That makes sense? So this is one part of the Earth's orbit to the other part of the Earth's orbit. This is the apparent shift in how much that star moves on the sky. And then the distance, well, okay, D equals r sine theta, that's geometry, equals r theta. Now I gotta have theta in radians. That's the only way that the small angle approximation makes sense. But I don't want it in radians, I want it in arc seconds. So how many radians are in an arc second? How many radians are in a circle? 2 pi. How many degrees are in a radian? 2 pi over 360. Other way around. I always have to do it first and then check if I'm right and realize that I'm wrong. Okay, so this is theta in radians. So we need to get this in. So D is r theta rad. But we need to get this in degrees, so we're going to multiply by 180 over pi degrees times 60 arc minutes in a degree times 60 arc seconds in a minute. And this gives me a number I should know that number off the top of my head. Ha! 206, that was almost right. This gives you a number that is 206,265. Why did I just write this number down? This is pi over 180 times 60 times 60. That's a stupid combination. Like, that's not something that I can do in my head. Something that I know all the time, because this is the relationship between AU and parsecs. Does that make sense? So this is also the conversion between astronomical units and parsecs, is this. And it just comes from geometry. So this is why a parsec is the most useful unit, because an AU is our base unit. It's our base ruler. That's what we can use. And then a parsec is the next thing that makes sense after that. You just convert convert degrees into arc minutes, and you get the size. So to find the distance in parsecs, you plug in the angle in arc minutes, or arc seconds, and then you're done. It's very easy. So I do have a challenge question here. This is one of the questions that you guys asked. Does everybody have a voter? I got a voter question. Let's do some math. I've got a couple extras if anybody's missing one. Is anybody else missing one? I should have walked down the other side. You can just always play the YMCA. You got one? You got one? I'm going to make these color at some point in time, but for now, black and white. Okay, while I'm doing this, we can all read the question up there. So the Keck telescope is one of the largest telescopes in the world, and it has an angular resolution. Say again, everybody? Right? Yeah. Has an angular resolution of 0.01 arc second. Remembering the parallax formula, what's the furthest thing that it can see? Is it a parsec from us, 100 parsecs from us, a kiloparsec from us, or a megaparsec from us? So everybody take a second and think. Okay, everybody, don't do math. Just look. Do the math in your head. You can do this math in your head. I suck at doing math in my head, so if I tell you that you can do the math in your head, it's really just moving a decimal point. Everybody? You're thinking too much. Just guess. All right. So kind of a couple of you changed your minds a couple of times, okay? All right, so take a second, discuss with your neighbor, if you guys could talk. Discuss with your neighbor and see if you're right or convince him that you are. Yes, you guys can talk in the back. Does everybody got a partner? We have an odd number of people.
This is still my guess. Yeah. So it's 100 over 1 flips. So 1 over, so that's 1 over 100 and then flip it and then it's 100.
All right, is everybody good? So we want to vote again? All right, everybody gets D, or B, sorry. So yeah, that's right. So you can see about 100 parsecs away with Keck, because as you said, I take this is 1 over 100, I just flip it over, and I get about 100 parsecs. So parallax for Keck doesn't get you very far. That's kind of a drag. The atmosphere is a big part of the problem, because the atmosphere is really tricky. So what we do is we send them to space. So there's an important satellite called Hipparcos. Hipparcos is one of the most important satellites that we've launched because it did a much, much better job measuring parallax to a bunch of stars because it could get above the atmosphere. And it doesn't have all the tricky things that Keck has. In 2014, Gaia launched, and Gaia is measuring, so the galaxy looks like this. Gaia, and here's the center, and here's us. Gaia sees about this much of the galaxy, which is a crap ton. This is billions and billions of stars that it's going to measure to the distances to extremely high accuracy. And even though the mission's not complete and the data is actually very difficult to work with, even still, we still learn enormous amounts about the galaxy. So we've learned about the mass of our galaxy by just measuring where the stars are, just measuring their stars very accurately. Okay, is that it for that? Okay, now how am I doing? 141. Now I'm going on to. Okay.
Wait, does it say it's orbiting L2 as well?
Yes, Gaia is at L2. Let me explain what L2 is, because that's a good question.
No, I just didn't know multiple objects could be at L2 at the same time.
Yeah, because L2 isn't really a place. It's an area. It's not a point. So let's talk about that. Yeah, there are. What is an L2 now? I think there's 4 things in L2 now. So okay. Here is the sun, and here is us. And what are the forces on us? There's the gravitational force from the sun, and the centrifugal force pushing outwards. And sometimes we hate the centrifugal force, and sometimes we love the centrifugal force. So okay, it's not really a force, it's a coordinate system, but it's effectively a force. Right? It works just like a force. So when these two things balance, then you have something that's stable. So the two forces balance at 5 points in the orbit of the Earth and the Sun. There's L1, which is right between Earth and the Sun. There's L2, which is outside the Earth, Sun. And then there's L3, which is here, and L4, which is here, and L5, which is over here. There are, I think there's a Trojan moon here. In the Sun-Earth, or in the Sun-Jupiter system, there's a bunch of Trojan moons in the L3 and L4 points. There's a little asterisk that's there. So L2 is this spot out here that is far away from the sun, more importantly, far away from the planet. And even more importantly, it's in orbit around the planet, so it can see the whole sky without the planet being in the way. So that's why Gaia is out there, so that it can see everything without having to deal with the planet being in the way. James Webb is out there because the planet's hot, and we don't want the heat of the planet to heat up the telescope. So James Webb is out there because it's colder over there. But L2, it's a funny spot. It's not a point in space. There's like a valley, and things orbit this kind of valley of gravitational potential. So it's kind of a funny spot. But there's a couple of satellites there. It's a very cool place. Okay. And the cool thing is it's a spot in empty space, and they just hit it with a rocket like it was nothing. Okay, where do the perihelion and aphelion formula come from? Hopefully I will show you. The DF shell business. I'm going to do that derivation. A couple of you asked about that, so I'm going to do that. Can you go over? That's the same question. Figure 2.8, that's the same question. Work energy, I'll do that too. Is there a reason that planetary motion is elliptical? Yes, I will do that Monday. Do objects with zero mass? And the question said zero mass or negligible mass. Negligible mass is still positive mass. The neutrino has negligible but not zero mass. Probably. Though I'm dubious. I don't know about the neutrino's mass. I don't like it. Anyway, because it doesn't couple to the Higgs, which is how everything else gets its mass. So the neutrino has to have a mass some other way. Anyway, that's, can we discuss the geometry of ellipse? I will. Work is the integral of force over time. No. Work is the integral of force over what? I'll come back to that. Distance. But I can turn it into time using what? How do I turn distance into time? With math. What's the math quantity that I like? I heard it. Speed, velocity, right? So I can turn them. I can turn those integrals into each other, which I'll show you. I'll discuss the geometry. Let's see. Oh, so this is a good question. How do astronomers prove that the laws are universal if we can't actually make any measurements anywhere else? Well, we can't, but yeah, we can, because we can see it. We can see stuff. One of my favorite measurements is a measurement of the fine structure constant. So the fine structure constant is 1 over 137, and it's a combination of the electron charge and the speed of light and the electron mass, and I can't remember exactly what else. Just because I should have looked it up beforehand, but I forgot to. The fine structure constant is a dimensionless constant that relates the fundamental properties of an atom. or quantum mechanics, really. And we can measure that, and we can measure how that changes over time. So we go try to measure the fine structure constant by looking at various lines in spectra. We'll talk a lot about spectra, but spectra are how we learn basically everything. So from a spectrum, I can learn how much iron is in a thing. I can learn about how much excited iron is in a thing. I can learn about different excitements of iron and how they're different. And I can learn about the ratios of those excitements. I'll explain all this later. And from those little details of the spectra of, say, iron in a star or whatever, we can tell whether or not the fine structure constant has changed over time. And it has not. So chances are the physics are the same everywhere all the time. But it's a tricky measurement to make. What are the known limitations of Newton's gravity? Well, it breaks down when anything gets too big or you get too close to it. So whenever something's escape energy gets large compared to the speed of light, not larger than, but a fair fraction, then you need to throw out Newtonian gravity and add on extra corrections. And it's, for the most part, they look like Newtonian gravity plus extra terms, but they come out of general relativity, which I'm not going to get into at all. How did Galileo discover X, Y, or Z? I have no idea, but the discovery process sometimes is, I think this thing works like this because of this, and you go look for thing C and you find it, and that's cool. Sometimes you have no idea what you're doing and you're just looking under rocks. I don't know how his discovery process works. That's an interesting idea. And also, how did the so the question was were Galileo and Newton just smarter than the rest of us? And no, because learning calculus is pretty hard. Inventing calculus is really hard. So he's got that going for us. I mean, so yeah, Newton was just smarter than all of us. I'm pretty happy just going out and saying that. But was he smarter than the smartest person now? Probably not. But there was only a couple of people on the planet at that point. So the whole geometry of the thing was different. So it's an interesting question. There are definitely people now who are incredibly bright, but are they making the same contributions that Einstein did or that Newton did? We don't know yet. So we'll find out. Which planet has the most elliptical orbit? I think it's Pluto. No, I'm sorry. I guarantee that it's Pluto because sometimes Pluto's inside Neptune and sometimes it's outside Neptune. How do you find the position and velocity vectors? I wasn't 100% sure what you meant by this question, but I can answer it. Position is a coordinate. And you find it by using the velocity. So you integrate the velocity to get the position, and you integrate the acceleration to get the velocity. So usually, if I want to know where something is, I need to know its velocity and then its acceleration. And I just do a couple integrals, and I'm sorted. Often it's a lot harder than that. If you meant something, whoever meant something different from this question, that's cool. You can ask again. Reference frames. So several of you asked about reference frames. A reference frame is anywhere that you can be at any velocity that isn't accelerating. So that means that it can be moving in one direction, but it can't turn. Does that make sense? So as soon as the velocity vector changes, then you're not in an inertial reference frame. So in this Sun-Earth system, if I treat it as it's not moving and I incorporate the Coriolis force, which pushes out that way, which maybe you guys haven't seen in detail yet, but we'll talk about it a little bit. So when I have this rotating system, I can just rotate my brain and fix the system, but then I pick up an extra force. That's because the rotating system is a non-inertial frame. It's accelerating. Rotating is accelerating, right? So the reference frame that you're in is really a mathematical convenience for the most part, but they're not all the same. Some reference frames are different. So if your reference frame is spinning, it doesn't work the same as a reference frame that's just sliding. We don't need to go too deep down that rabbit hole yet, but I wanted to put some. Why did Kepler figure out the planetary orbits based on the Mars and Sun? And I'm not sure if the question was why did he do it at all, or why did he use the Mars and Sun. Mars is basically visible all the time, and it's close, and it goes around pretty quick. So, and you can see it at night. Venus is harder to use because it goes down. It's close to the sun. but Mars is up most of the night. Also, I'm alive for many Mars orbits. I'm not alive for many Jupiter orbits. Right? How long? What's Jupiter's orbit? It's like 200 years, right? So, what's the difference between all these primes? They're just shorthand. They're just sweeping crap under the rug. That K in the first place was, here's a letter for things that I don't understand. And then they put a prime on it for other things that I don't understand, or slightly different things. Ultimately, they all turn into G, and that's the important thing. What is sidereal time? I did not talk about sidereal time, and I need to, but I rarely think about it. So how many, in the period of one day, the Earth rotates through a number of degrees? From midnight today to midnight tomorrow, how many degrees does the Earth rotate through?
Slightly more than 360.
361. So slightly more than 360. Why? Why not 360? I'm going to draw a really exaggerated diagram. So here is the Earth. Here is the Earth that has rotated 360 degrees. It's not pointing at the sun anymore, is it? Sidereal time is the rotation of this planet taking 360 degrees. So it's when one point of the sun is looking at the same RAN deck. But the RAN deck for the sun moves every day. But if you want to pick a point, the time that the next RAN deck is one sidereal day, which is a little bit longer than a solar day. I don't need to think about these at all anymore, but you're going to run into it at some point in time. So it's not. I'm not going to use sidereal time at all for any of this. I explained that. Okay, this is a good question. Variables can get tricky. One of you, and actually plenty of you, several of you are from engineering, and some of you from, like not all of you are from math or physics. So this is a known thing. So for instance, this student has known U as the variable for internal energy. I do that too. Would it be possible to have a table of variables? Yes, that is a good idea. You should make one. I'm not going to do it for you because then you'll get my interpretation of things, and you got to have your own relationship with all these variables because these variable names are all context-based. And that's the important bit is when you start a problem and you've got these variables, you've got to think about what context here is because I also am going to use U for being internal thermal energy when I get there, when I need to. So there's not enough letters. So, but yes, this is actually a great idea, and I really recommend everybody do it. Make a table of the variables that you come across and what symbols that we use. Start it now and leave it at the front of your book because a lot of these things are going to come up again. That's a very good idea. I hope that didn't come out as snarky, more encouraging. Ellipsis math, I'll talk about ellipsis math right now. So, any questions on the questions? I hope I covered everything. Now I have 15 minutes. Shoot. Might have to rethink how I'm doing questions. I like doing it that way because I feel like it engages me with what you guys are thinking, but it takes time. Okay, so Tycho Brahe came up with a lot of amazing data, and Kepler came up with these 3 laws. So these 3 laws are crucial for our understanding of space. And very useful. And really the third one is the most important one. The first 2 are observations, and the third one is the one that we can really use. Like that's the one that we use all the time. So the 3 laws. Planets follow elliptical paths. Why? I'll show you. Mostly, it's because of the exchange of kinetic and potential energy. It's because it's an oscillator. The second one, elliptical paths with the sun at one focus. The second one, this was curious. I don't have any idea how he sorted out this law from the ground. I mean, it's kind of gorgeous. I mean, you had to come up with the first one first, and then once you understand the first one, the second one will show up. But it says that planets sweep out equal areas for equal time. Now I'm going to draw this in a very exaggerated fashion. So, you know, what's the area of a triangle? I'm going to draw some triangles. Is that
1/2 base times height.
1/2 base times height. Right? However you manage to measure that. So when I'm looking at an arc length here, if I've got a length of arc here, that sweeps out, if I go, sorry, let me start that again. So I'm going to go around this ellipse on my planet. So I start out here, and after a certain time later, I'm over here. So that's going to be V delta T, right? And that sweeps out some area. And then later on, I'm going to go from here to here, and I'll have some other V delta T. Let's say the delta T is the same, but V is not. Later on, I'm going to sweep out some more area. And then later on, let's do this one over here. As I go from here to here, I'm going to travel V delta T. And I'm going to sweep out another area. So, but this arm length is longer, so H is higher. Right? Now, if planets sweep out equal time for equal area, then the base has to be shorter if H is higher, right? So if my time interval is the same, what does that say about the velocity? It's lower. When I'm over here, the velocity is lower than when I'm over here. But he says more than that, more than just the velocity gets lower as you go over there. It gets lower in a very particular way, in a way that keeps area constant. And I'll show you why that is on Monday. Probably it's going to be Wednesday, because I don't think I'm going to get to Monday. Okay, so that's very useful. So, do I have a thing? Yeah, so, and the, let's see, I don't think I need to say anything else about that. The last one, the period, is related to the semi-major axis as p squared equals ka cubed. And this has this very nice, in dimensional units, if p is in years squared, and a is in AU cubed, there's no constant here. Now I know this to be true because the Earth takes 1 year to go around the sun, and it's at a distance of 1 AU, right? So if I plug in 1 year and 1 AU, I get 1 equals 1, and that's kind of trivially true. The nice thing is this works out for every other planet as well, as long as you keep the units right. Does anybody have any questions about those three laws? Yeah.
What are K and X?
Oh, sorry. K is the semi-major axis. A is, I don't know what I just said. A is the semi-major axis. K is a constant. That really depends on units. This is just your units conversion. If you use P in years and A in astronomical units, then there's no K. So let's talk about ellipses for a second. So, okay, I always have a hard time remembering which one's perihelion and which one's periastron. It occurred to me recently that Perry the platypus is always very close to Dr. Doofenshmirtz. So we'll go with Perry the platypus as our mnemonic to remember where periastron is. And if you did not grow up with Phineas and Ferb, I'm very sorry. I didn't grow up with Phineas and Ferb, but I did watch it a lot one night after I grew up because it's a brilliant cartoon. Okay, so a circle. A circle is easy. A circle is all the points that are a distance r from another point. It is the simplest thing you can do. I don't know if that's true, but it's a very simple thing. The second simplest thing you can do is say, okay, I got 2 points, and I got a line from each one of those. And we're going to call these R and R prime. And I'm going to say, okay, here's the center. We're going to call this semi-major axis A. The semi-major axis is the only unit that I care. I don't really care about the semi-minor axis. Semi-major axis we'll call A. And we're going to put each one of these points a distance away from the center, a fraction of A up the arm length, right? So we're going to call this distance A times E. So this is the definition of E. E is the fraction of the semi-major axis that the focus is, along which. Wasn't a very good sentence. I'm not an Englishman. So this distance here is A times E. That defines the eccentricity. The eccentricity is related to several other quantities as well, but we'll go with this as the definition. It's the distance here relative to the distance total. Right? Now, that's all I've defined so far, is a semi-major axis and a point. And then another one, the same semi-major axis. The circle is defined as the set of points such that R, the distance, let's call that one R and this one R prime. R, the distance from the first focus, plus R prime, the distance to the second focus, R plus R prime, is a constant, 2A. So everywhere along this ellipse, the sum of the distance to the first focus plus the distance to the second focus is twice the semi-major axis. Does that make sense? That's how you make an ellipse. You take 2 points, and the distance between the two is twice some other number. That defines the ellipse. So we can define some other properties of the ellipse that we'll need. So for instance, the semi-minor axis, B. How long is the semi-minor axis? Well, it's a property of the ellipse, and we can get it from the semi-major axis and the eccentricity by saying, I'm going to erase this and then redraw it a little bit more carefully. Here's the center. I'm going to take a point immediately above the center. By definition, that's the semi-minor axis. And then if I say, well, I want this distance and this distance, call this one R prime and this one R. Well, this is geometry, and I can just use Pythagoras, right? So the horizontal leg is AE, so the long leg is R, so R squared equals A squared E squared plus B squared. And then you solve for B, and you find, regardless, it's getting late and watching me do algebra is dumb, and I'm going to make you do it for homework anyway. So, if you do the geometry right, this distance here is A squared times 1 minus E squared. And you can see the behavior makes sense. If I send E to 0, that's sending these 2 points to each other. B squared just becomes A squared, and that's just a circle again. Okay. Similarly, through geometry that I'm going to make you do for homework, you can get rid of R prime. So R prime is the distance to the other focus. You can just algebraically get rid of R prime and write down write down a function for R, getting rid of R prime. And it's a little bit of geometry, but it's not that hard, but it's a homework problem. There's a homework, it's due next Friday. It will be up by 5 o'clock today, I promise. If it's not up by 5 o'clock today, then I'll give you then the homework will be due a little later. But some of it's going to be some geometry with ellipses, just so that you have that in your hands. Specifically this one, because I'm going to use this one to show that planets move on elliptical orbits on Monday or Wednesday. So R is the semi-major axis times this quantity 1 minus E squared over 1 plus E times the cosine of theta, where theta is measured here. So the point here R, the distance between here and here, is equal to this formula, which I'm not going to drive. I'm going to make you drive. And then similarly, the area of a circle is pi times the semi-major axis times the semi-minor axis, which is a very handy formula. Let's see. Does anybody have any questions about ellipses? Yeah.
So what is perihelion?
That's perihelion. So there's 2 points that are important, perihelion and aphelion. And I can't remember which one's perihelion, which is aphelion, but perihelion has perihelion. Perihelion is the closer of the two.
To the point along the
To the focus. Okay. Sorry, to the focus. So this is where the sun is.
Okay.
Sorry, so the sun lives at one of the foci, and the closest point to the sun is perihelion, and the furthest point to the sun is aphelion. And it's important to drill into your head which is which, because otherwise you have to stop and think about it every time. Yeah, that's right.
I just think about apotheosis because it's ascending to God. So you ascend to the higher belief above this.
All right, that works pretty good. I like that. Okay, ellipses, let's see. How much can I cram in? I got 2 more minutes to talk. What else do I have? We're not going to do that. Okay, so in 2 minutes I'm going to go through Kepler. I'm going to go through Newton's 3 laws. You guys all took physics, so I don't actually need to spend a ton of time on it, but I'm going to go through it. I'll go through the horrid math in a second. Newton has 3 laws. If it's sitting there, it's going to keep sitting there. If I threw it, it'll keep flying until it hits the wall. F equals ma. Kind of just says that, really. And action and reaction, that one's important. That one says this is the opposite if you're looking the other way. So stuff has mass, and mass keeps things from moving if they don't want to. F equals ma and action and reaction. So the one of the important bits is Newton's gravity. So the gravitational force, so the thing that he invented was the force. Well, he said, okay, there's a force and that's going to do something, and then there's an acceleration that's a response. So what does this say? So what does F equals ma say? So A is the response of a thing to some external force. And the proportionality constant, how much response you get, is just the definition of the mass. Now, I have this gravity, and weirdly I put a mass in here too. I have no idea why I get to use the same mass in this equation as I do in this equation. And if you can solve that problem, you'll be more famous than God. Because no one else can solve that either. No joke. If you can sort out why the mass in gravity is the same as the mass for kicking a ball down the road, that's one of the big unsolved problems in physics. So the force between 2 objects is some proportionality constant we call G, which is just our ignorance of units. So the universe cares about units. It doesn't care about meters, but it cares about how things are related. So G is just units. M is a mass of one object, little m is the mass of the other object. It doesn't matter, it could be bigger. And R is the distance between them, and I wrote it in this way. The book doesn't write it in this way, and it kind of bugs me, because this is really how it should be written. Force is a vector, and it's directed along r hat, where r hat is the unit vector between the 2 objects, and it's minus that. So if I'm looking at the other object, I get the same formula because the r hat will be in the other direction if I switch objects. Okay, and now I'm out of time, so I am going to pick up with this question. If there's spherical symmetry, then I can treat all the mass as though we're at the center, and 4 or 5 of you asked about that math because it's kind of hairy. So I'll go over that on Monday. Homework due next Friday. Yeah, that's it. Have a good day.